In computer operating systems, paging is one of the memory management schemes by which a computer can store and retrieve data from secondary storage for use in main memory. In the paging memory management scheme, the operating system retrieves data from secondary storage in same-size blocks called pages. The main advantage of paging over memory segmentation is that it allows the physical address space of a process to be non-contiguous. Before paging came into use, systems had to fit whole programs into storage contiguously, which caused various storage and fragmentation problems. Paging is an important part of virtual memory implementation in most contemporary general-purpose operating systems, allowing them to use secondary storage for data that do not fit into physical random access memory. Page faults. The main functions of paging are performed when a program tries to access pages that are not currently mapped to physical memory. This situation is known as a page fault. The operating system must then take control and handle the page fault, in a manner invisible to the program. Therefore, the operating system must determine the location of the data in secondary storage. Obtain an empty page frame in RAM to use as a container for the data. Load the requested data into the available page frame. Update the page table to refer to the new page frame. Return control to the program, transparently retrying the instruction that caused the page fault. If there is not enough available RAM when obtaining an empty page frame, a page replacement algorithm is used to choose an existing page frame for eviction. If the evicted page frame has been dynamically allocated during execution of a program, or if it is part of a program's data segment and has been modified since it was read into RAM, it must be written out to a location in secondary storage before being freed. Otherwise, the contents of the page's frame in RAM are the same as the contents of the page in its secondary storage, so it does not need to be written out to secondary storage. If, at a later stage, a reference is made to that memory page, another page fault will occur and another empty page frame must be obtained so that the contents of the page in secondary storage can be again read into RAM. Efficient paging systems must determine the page frame to empty by choosing one that is least likely to be needed within a short time. There are various page replacement algorithms that try to do this. Most operating systems use some approximation of the least recently used page replacement algorithm or a working set-based algorithm. To further increase responsiveness, paging systems may employ various strategies to predict which pages will be needed soon. Such systems will attempt to load pages into main memory preemptively, before a program references them. Page replacement algorithms. Demand paging. When pure demand paging is used, page loading only occurs at the time of the data request, and not before. In particular, when demand paging is used, a program usually begins execution with none of its pages preloaded in RAM. Pages are copied from the executable file into RAM the first time the executing code references them, usually in response to page faults. As a consequence, pages of the executable file containing code not executed during a particular run will never be loaded into memory. Anticipatory paging, this technique, sometimes also called swap prefetch, preloads a process's non-resident pages that are likely to be referenced in the near future. Such strategies attempt to reduce the number of page faults a process experiences. Some of those strategies are if a program references one virtual address which causes a page fault, perhaps the next few pages worth of virtual address space will soon be used, and if one big program just finished execution, leaving lots of free RAM, perhaps the user will return to using some of the programs that were recently paged out. Free page queue. The free page queue is a list of page frames that are available for assignment after a page fault. Some operating systems support page reclamation. If a page fault occurs for a page that had been stolen and the page frame was never reassigned, then the operating system avoids the necessity of reading the page back and by assigning the unmodified page frame. Page stealing. Some operating systems periodically look for pages that have not been recently referenced and add them to the free page queue, after paging them out if they have been modified. Pre-cleaning. Unix operating systems periodically use sync to pre-clean all dirty pages, that is, to save all modified pages to hard disk. Windows operating systems do the same thing via modified page writer threads. Pre-cleaning makes starting a new program or opening a new data file much faster. The hard drive can immediately seek to that file and consecutively read the whole file into pre-cleaned page frames. Without pre-cleaning, the hard drive is forced to seek back and forth between writing a dirty page frame to disk, and then reading the next page of the file into that frame. Thrashing. Most programs reach a steady state in their demand for memory locality both in terms of instructions fetched and data being accessed. This steady state is usually much less than the total memory required by the program. This steady state is sometimes referred to as the working set, the set of memory pages that are most frequently accessed. Virtual memory systems work most efficiently when the ratio of the working set to the total number of pages that can be stored in RAM is low enough that the time spent resolving page faults is not a dominant factor in the workload's performance. A program that works with huge data structures will sometimes require a working set that is too large to be efficiently managed by the page system, resulting in constant page faults that drastically slow down the system. This condition is referred to as thrashing. Pages are swapped out and then accessed, causing frequent faults. An interesting characteristic of thrashing is that as the working set grows, there is very little increase in the number of faults until the critical point. An extreme example of this sort of situation occurred on the IBM System/360 Model 67, and IBM System/373Z architecture, mainframe computers. An execute instruction that crosses a page boundary could point to a move instruction that also crosses a page boundary, and the move instruction could move data from a source that crosses a page boundary to a target of data that also crosses a page boundary. The total number of pages thus being used by this particular instruction is 8, and all 8 pages must be present in memory at the same time. If the operating system will allocate less than 8 pages of actual memory in this example, when it attempts to swap out some part of the instruction or data to bring in the remainder, the instruction will again page fault, and it will thrash on every attempt to restart the failing instruction. To decrease excessive paging, and thus possibly resolve thrashing problem, a user can do any of the following: increase the amount of RAM in the computer, decrease the number of programs being concurrently run on the computer. The term thrashing is also used in contexts other than virtual memory systems, for example to describe cache issues in computing or silly window syndrome in networking. Sharing. In multi-programming or in multi-user environment, it is common for many users to be executing the same program. If individual copies of these programs were given to each user, much of the primary storage would be wasted. The solution is to share those pages that can be shared. Sharing must be carefully controlled to prevent one process from modifying data that another process is accessing. In most systems, the shared programs are divided into separate pages, that is, coding and data are kept separate. This is achieved by having page map table entries of different processes point to the same page frame. That page frame is shared among those processes. Terminology. Historically, paging sometimes referred to a memory allocation scheme that used fixed-length pages as opposed to variable-length segments, without implicit suggestion that virtual memory techniques were employed at all or that those pages were transferred to disk. Such usage is rare today. Some modern systems use the term swapping along with paging. Historically, swapping referred to moving from to secondary storage a whole program at a time, in a scheme known as roll-in roll-out. In the 1960s, after the concept of virtual memory was introduced in two variants either using segments or pages, the term swapping was applied to moving, respectively, either segments or pages, between secondary storage and memory. Today, with a virtual memory mostly based on pages, not segments, swapping became a fairly close synonym of paging, although with one difference. In systems that support memory-mapped files, when a page fault occurs, a page may be then transferred to or from any ordinary DASD file, not necessarily a dedicated space. Page-in is transferring a page from secondary storage to RAM. Page-out is transferring a page from RAM to secondary storage. Swap in and out only refer to transferring pages between RAM and dedicated swap space or swap file or scratch disk space, and not any other place on secondary storage. On Windows NT-based systems, dedicated swap spaces known as a page file and paging swapping are often used interchangeably. Implementations. Ferranti Atlas. The first computer to support paging was the Atlas, jointly developed by Ferranti, the University of Manchester and Plessey. The machine had an associative memory with one entry for each 512-word page. The supervisor handled non-equivalence interruptions and managed the transfer of pages between core and RAM in order to provide a one-level store to programs. Windows 3X and Windows 9X. Paging has been a feature of Microsoft Windows since Windows 3.0 in 1990. Windows 3X creates a hidden file named 386SPART-PAR or WIN386SWP for use as a swap file. It is generally found in the root directory, but it may appear elsewhere. Its size depends on how much swap space the system has. If the user moves or deletes this file, a blue screen will appear the next time Windows is started, with the error message "The permanent swap file is corrupt." The user will be prompted to choose whether or not to delete the file. Windows 95, Windows 98 and Windows ME use a similar file, and the settings for it are located under Control Panel. A system or performance tab of virtual memory. Windows automatically sets the size of the page file to start at 1.5 the size of physical memory, and expand up to 3 physical memory if necessary. If a user runs memory-intensive applications on a system with low physical memory, it is preferable to manually set these sizes to a value higher than default. Windows NT, the file used for paging in the Windows NT family is PageUALS. The default location of the page file is in the root directory of the partition where Windows is installed. Windows can be configured to use free space on any available drives for PageUALS. It is required, however, for the boot partition to have a PageUAL on it if the system is configured to write either kernel or full memory dumps after a blue screen of death. Windows uses the paging file as temporary storage for the memory dump. When the system is rebooted, Windows copies the memory dump from the PageUAL to a separate file and frees the space that was used in the PageUAL. Fragmentation. In Windows default configuration, the PageUAL is allowed to expand beyond its initial allocation when necessary. If this happens gradually, it can become heavily fragmented, which can potentially cause performance problems. The common advice given to avoid this is to set a single lock PageUAL size so that Windows will not expand it. However, the PageUAL only expands when it has been filled, which, in its default configuration, is 150% the total amount of physical memory. Thus the total demand for PageUAL-backed virtual memory must exceed 250% of the computer's physical memory before the PageUAL will expand. The fragmentation of the PageUAL that occurs when it expands is temporary. As soon as the expanded regions are no longer in use, the additional disk space allocations are freed and the PageUAL is back to its original state. Locking a page file's size can be problematic in the case that a Windows application requests more memory than the total size of physical memory in the page file. In this case, requests to allocate memory fail, which may cause applications and system processes to fail. Supporters of this view will note that the page file is rarely read or written in sequential order, so the performance advantage of having a completely sequential page file is minimal. However, it is generally agreed that a large page file will allow use of memory-heavy applications, and there is no penalty except that more disk space is used. The extra disk space may be trivial on systems using current specifications, that is a system with 3 GB of memory having a 6 GB fixed-size swap file on a computer with a 750 GB disk drive, or a system with 6 GB of memory/16 GB fixed swap and 2 TB of disk space. In both cases the system is using about 0.8% of the disk space with the swap file pre-extended to maximum. Defragmenting the page file is also occasionally recommended to improve performance when a Windows system is chronically using much more memory than its total physical memory. This view ignores the fact that, aside from the temporary results of expansion, the PageUAL does not become fragmented over time. In general, performance concerns related to PageUAL access are much more effectively dealt with by adding more physical memory. Unix and Unix-like systems, Unix systems, and other Unix-like operating systems, use the term swap to describe both the act of moving memory pages between RAM and disk, and the region of a disk the pages are stored on. In some of those systems, it is common to dedicate an entire partition of a hard disk to swapping. These partitions are called swap partitions. Many systems have an entire hard drive dedicated to swapping, separate from the data drive, containing only a swap partition. A hard drive dedicated to swapping is called a swap drive, or a scratch drive, or a scratch disk. Some of those systems only support swapping to a swap partition. Others also support swapping to files. Linux. From the end-user perspective, swap files in versions 2.6x and later of the Linux kernel are virtually as fast as swap partitions. The limitation is that swap files should be contiguously allocated on their underlying file systems. To increase performance of swap files, the kernel keeps a map of where they are placed on underlying devices and accesses them directly, thus bypassing the caching and avoiding the file system overhead. However, Red Hat recommends swap partitions to be used. When residing on HDDs, which are rotational magnetic media devices, one benefit of using swap partitions is the ability to place them on contiguous HDD areas that provide higher data throughput or faster seek time. However, the administrative flexibility of swap files can outweigh certain advantages of swap partitions. For example, a swap file can be placed on any mounted file system, can be set to any desired size, and can be added or changed as needed. Swap partitions, however, are not that flexible. For example, a swap partition cannot be enlarged without using partitioning or volume management tools, which introduce various complexities and potential downtimes. The Linux kernel supports a virtually unlimited number of swap backends, supporting at the same time assignment of backend priorities. When the kernel needs to swap pages out of physical memory, it uses the highest priority backend with available free space. If multiple swap backends are assigned the same priority, they are used in a round-robin fashion, what provides improved performance as long as the underlying devices can be accessed efficiently in parallel. OS X uses multiple swap files. The default installation places them on the root partition, though it is possible to place them instead on a separate partition or device. Solaris allows swapping to raw disk slices as well as files. The traditional method is to use slice 1 on the OS disk to house swap. Swap setup is managed by the system boot process if there are entries in the VFSTAB file, but can also be managed manually through the use of the swap command. While it is possible to remove, at runtime, all swap from a lightly loaded system, Sun does not recommend it. Recent additions to the ZFS file system allow creation of ZFS devices that can be used as swap partitions. Swapping to normal files on ZFS file systems is not supported. Amiga OS 4.0 introduced a new system for allocating RAM and defragmenting physical memory. It still uses flat shared address space that cannot be defragmented. It is based on slab allocation method and paging memory that allows swapping. Paging was implemented in Amiga OS 4.1 but may lock up system if all physical memory is used up. Swap memory could be activated and deactivated any moment, allowing the user to choose to use only physical RAM. Performance. The backing store for a virtual memory operating system is typically many orders of magnitude slower than RAM. Additionally, using mechanical storage devices introduces delay, several milliseconds for a hard disk. Therefore it is desirable to reduce or eliminate swapping, where practical. Some operating systems offer settings to influence the kernel's decisions. Linux offers the sysswappiness parameter, which changes the balance between swapping out runtime memory, as opposed to dropping pages from the system page cache. Windows 2000, XP, and Vista offer the Disable Paging Executive Registry setting, which controls whether kernel mode code and data can be eligible for paging out. Mainframe computers frequently used head per track disk drives or drums for page and swap storage to eliminate seek time, and several technologies to have multiple concurrent requests to the same device in order to reduce rotational latency. Flash memory has a finite number of erase write cycles, and the smallest amount of data that can be erased at once might be very large, seldom coinciding with page size. Therefore, flash memory may wear out quickly if used to swap space under tight memory conditions. On the attractive side, flash memory is practically delayless compared to hard disks, and not volatile as RAM chips. Schemes like ReadyBoost and Intel Turbo Memory are made to exploit these characteristics. Many Unix-like operating systems allow using multiple storage devices for swap space in parallel, to increase performance. Swap space size. In some older virtual memory operating systems, space in swap backing store is reserved when programs allocate memory for runtime data. Operating system vendors typically issue guidelines about how much swap space should be allocated. Reliability. Swapping can decrease system reliability by some amount. If swap data gets corrupted on the disk, the memory will also have incorrect contents after the data has later been returned. Addressing limits on 32-bit hardware. Paging is one way of allowing the size of the addresses used by a process, which is the process's virtual address space, or logical address space, to be different from the amount of main memory actually installed on a particular computer, which is the physical address space. Main memory smaller than virtual memory. In most systems, the size of a process's virtual address space is much larger than the available main memory. The amount of physical main memory available is limited by the number of address bits on the address bus that connects the CPU to main memory. There might be fewer physical address bits than virtual address bits. For example, the i386SX CPU internally uses 32-bit virtual addresses but has only 24 pins connected to the address bus, limiting addressing to at most 16 MB of physical main memory. Even on systems that have the same or more physical address bits as virtual address bits, often the actual amount of physical main memory installed is much less than the size that can potentially be addressed, for financial reasons or because the hardware address map reserves large regions for I/O or other hardware features, so main memory cannot be placed in those regions. Main memory the same size as virtual memory. It is not uncommon to find 32-bit computers with 4 GB of RAM. The maximum amount of RAM addressable unless the page table entry format supports physical addresses larger than 32 bits. For example, on 32-bit x86 processors, the physical address extension feature is required to access more than 4 GB of RAM. For some machines, for example, the IBM S/370 in XA mode, the upper bit was not part of the address and only 2 GB could be addressed. Paging and swap space can be used beyond this 4 GB limit, due to it being addressed in terms of disk locations rather than memory addresses. While 32-bit programs on machines with linear address spaces will continue to be limited to the 4 GB they're capable of addressing, because they each exist in their own virtual address space, a group of programs can together grow beyond this limit. On machines with segment registers, for example, the access registers on an IBM System/370 in ESA mode, the address space size is limited only by OS constraints, for example, the need to fit the mapping tables into the available storage. Main memory larger than virtual address space. A few computers have a main memory larger than the virtual address space of a process, such as the Magic 1, some PDP-11 machines, and some systems using 32-bit x86 processors with physical address extension. This nullifies a significant advantage of virtual memory, since a single process cannot use more main memory than the amount of its virtual address space. Such systems often use paging techniques to obtain secondary benefits. The extra memory can be used in the page cache-to-cache frequently used files and metadata, such as directory information, from secondary storage. If the processor and operating system support multiple virtual address spaces, the extra memory can be used to run more processes. Paging allows the cumulative total of virtual address spaces to exceed physical main memory. A process can map its data structures to main memory-backed files, such as files on the Linux TMPFS file system. the size of the cumulative total of virtual address spaces is still limited by the amount of secondary storage available. See also: Notes. References. External links, Windows Server, Moving PageURL to another partition or disk by David Nudelman, How Virtual Memory Works from HowStuffWorks.com, Linux Swap Space Management, Guide on Optimizing Virtual Memory Speed. References 8, 9, and 11. Virtual Memory Page Replacement Algorithms, Windows XP. How to manually change the size of the virtual memory paging file, Windows XP. Factors that may deplete the supply of paged pool memory, SwapFS driver that can be used to save the paging file of Windows and a swap partition of Linux.